Good afternoon, ladies and gentlemen. And we want to know the interaction between MR and CO₂-rich sulfate solution, interaction during the supercritical CO2 condition, and to quantify the geochemical processes. So, after the CO2 injection in a limestone reservoir rock, there is the case of Hontomín in Spain. We want to know to lead the possibility of the CO2 leakage through fracture in a marble caprock promoted the geochemical processes. So which geochemical processes may lead to the CO2 leakage through the fracture in the caprock? So first is the dissolution of the mineral composing the caprock that may lead to an increase in fracture dimensions, and also can lead to unsealing of fracture and increase in leak rate. So the second is the precipitation of secondary minerals, which also can allow the sealing of fractures. So these geochemical changes can lead to change in rock porosity and fracture permeability, and also in the seal capacity of the caprock. So therefore, our strategy is to perform percolation experiment with fracture cores at in situ conditions of partial total pressure of 150 bar, temperature of 60 degrees Celsius, the concentration of CO2 of 0.65 mol per kilograms, which is equivalent to the partial pressure of CO2 of 61 bar. And we use a sulfate-rich solution that was equilibrated with respect to calcite and gypsum. And also we performed the experiment at 3 different flow rates, 0.1, 1 and 60 milliliters per hour. And also we do the 2D reactive transport modeling in order to quantify the processes by matching the experimental data. So we characterize the initial sample by XRD and Rydberg analysis, and also by ESAM analysis. And we can observe that the initial MAR is mainly composed of calcite, less amount of quartz, illite, albite, gypsum and clinochlore, and insignificant amount of anhydrite and pyrite. So the ESAM image showed the morphology of the mineral grains. There is mainly of calcite. We can see the clinochlore and illite, and also the grains of pyrite. The initial porosity of the rock was between 5 and 7%, and the permeability was less than 10 to minus 18 meters square. And so therefore, it was an impermeable rock. So leak can only occur through the fractures. So we can also measure we propose to measure the variation in fracture permeability. So we prepared the core samples, which has a dimension of 7.5 milliliters of diameters and 90 milliliters of length, and have a synthetic fracture of around 10 microns. And we place the sample into the experimental setup. And the experimental setup composed of 2 pumps in which we mix the CO2 with the solutions. And then we measure the pressure on the inlet and at the outlet. And also we collect the output sample to thereafter analyze by ICP analysis. We developed this experiment in the University of Montpellier, and we work in situ conditions. So as I told you before, we work with a different flow rate and also with a different time duration. And also the residence time, it was different for the different flow rate. So we measure the pressure at the inlet and the outlet, and we can calculate the aperture of the fracture and also the fracture permeability. So when we place the CO2 with the solution, lead the solution acidification. So when we plot the variation in concentration of calcium with respect to time, we can see that the output concentration is greater than the input concentration that is attributed to the calcite dissolution. So when we plot the variation in sulfur concentration with respect to time, we can see that the deficit at the output concentration becomes from the gypsum precipitations. And when we plot the variation of iron and silicon concentration with time, the excess of iron is attributed to clinochlore dissolution, and the excess of silicon concentration is attributed to albite and clinochlore dissolution. So the quartz and illite dissolution was negligible, and the ratio between the iron and silicon from the clinochlore give us a silicon deficit. So we can say the likely precipitation of silicon-bearing minerals, which, for example, can be kaolinite. So based on the ESM, and microtomography image, ESM that add image of the 6 sections that are parallel to the flow, and microtomography image that are perpendicular to the flow, that we can see in this picture. So it gives of an observation of dissolution patterns that we can have. And we can observe that at low flow rate of 0.1, 0.2, and 4 Peclet number, we have phase dissolution. And when we have 1 milliliter per hour of flow rate, we have uniform dissolution to thereafter become wormhole, and then thereafter uniform. So when we increase the flow rate, we have at the microtomography image, we can see the homogeneous dissolution. So when we see the alteration of the fracture walls, we can see that at low flow rates, some reactive zone formed because remaining silicon minerals are inside. And also we can see by the ESM image the gypsum precipitates along the fracture. And when we increase the flow rate, high porous zone is formed because maybe some particles dragging. So when we plot the variation of permeability of the fracture with time, we can observe that at low flow rate, the permeability decreases with time, and it is attributed to gypsum precipitation. And when we increase the flow rate, the permeability also increases. So we develop a 2D reactive transport modeling in order to quantify the variation in aqueous chemistry and altered fracture walls. So we use the crunch flow code, and we perform just a half of the core. And we have two zones. One that is a high permeable zone, that is a fracture, and the rock, that is we're going to call now the distance normal to fracture. So in the fracture zone, the transport is controlled by advection, while the distance normal to fracture is controlled by diffusion. So in the model, we use the initial condition, the same that in situ condition in the experiments, and the water places into the model was, for the initial water was the same, with a partial pressure of 61 bars, and which has a pH of 3.3 approximately. And the initial pore water is a water equilibrated with respect to calcite and gypsum and have a pH of 7.7. So the transport parameter used was fixed the effective diffusion coefficient, and the initial mineral surface area was almost the same that calculated by the geometry. So when we plot the simulation of the cation concentration with time, we can observe that match the experimental data. So we plot the volume fraction of mineral with respect to the distance normal to fracture. And we can observe that in calcite, the main processes that occur is calcite dissolution and gypsum precipitation. And the light blue indicates the inlet of the core, and the dark blue indicates the outlet of the core. And we can see that the reactive zone calculated by the simulations almost match the observed one by ISAM image. Also in the model, we can see that clinochlore dissolves, and less amount of albite, and also kaolinite precipitates. So when we plot the volume of calcite with respect to the distance normal to fracture, we can observe that when we, at different flow rate, when we increase the flow rate, the difference between the inlet and outlet reduce. So it seems to match with the ISAM observation. By at low flow rate, phase dissolution was taking place, while a high flow rate, uniform dissolution was taking place. So when we plot the porosity, the variation of porosity with time at the three different flow rates, we can observe that always increase in porosity close to the fracture. So only increasing only increasing in permeability for faster flow rate. So the possible that at low flow rate the permeability decrease can be due to the possible pore structure change due to gypsum precipitation and movement or particle dragging of the mineral grains. So the main processes that occur is the dissolution of calcite, clinochlore and albite, precipitation of gypsum and clinochlore, formation of unaltered porous zones, and decreasing the main observation was decreasing in fracture permeability under slow flow rate despite an increase in porosity. That is important CL performance. So this is the simulation using the rate law from the literature, geometric surface area, and the initial effective diffusion coefficient, and clear effect of increasing of flow rate of the evolution of the fracture from phase dissolution to uniform dissolution.
Okay, so one very quick question, if there are.
why did calcite dissolve when you fed you had a calcite saturated solution on the inlet?
Yeah.
So why did calcite dissolve in the core? I thought you said that you were putting in the calcite saturated solution.
It's under saturation, the calcite, the solution, yeah.
Okay, so let's thank the speaker.
Yeah, thank you very much.